Thank you. Good morning, everyone. My name is Szehon Ho. The topic of my talk is going to be Hive and Spark. And first, I will try to introduce myself and my company that I work for. So I come from Cloudera. So I work in the Palo Alto office in Cloudera. And our company has a distribution of Hadoop called CDH. And basically, we bundle Hadoop along with dozens of other open source projects that work together very well with Hadoop. And on top of that, we also sell some enterprise and management security tools for people to use with their Hadoop cluster. In Cloudera, I am a member of the Hive team. So we have a lot of people working on different projects. I work on a project called Hive. As part of my job, I'm also working with the Hive community, which is a very big worldwide community of people working on the product. So I'm a committer and PMC on the project. And a little thing about myself, I'm very excited to be here in Berlin. I visited Germany last year. I really liked it. And I'm very grateful for Berlin Buzzwords to give me the opportunity to come back here. And hopefully this talk will also be interesting to some people here. So the talk is going to be split into 3 parts. First is a background. Hive, what is Spark, and why we think Hive and Spark is a good project. Then some technical deep dive into the project, some of the details. And finally end with a user view, like how this project will help users of Hive get better performance out of their jobs. So first is about Hive. What is Hive? Hive really is a project that came with the whole Hadoop kind of revolution in 2005 when the open source version of Google's MapReduce was first introduced to the world as an Apache project. At that time, it was quite a groundbreaker because a lot of organizations had this need to process huge amounts of data, and the open source version of MapReduce allowed them to do so, to scale to thousands of nodes and terabytes of data. So a lot of web companies like Yahoo, Facebook, LinkedIn, they all took this up, but really there was a need as part of this project to have a SQL access layer because a lot of people still, I mean, MapReduce you can write programs against, but in order to bring MapReduce the power to ordinary people who might not program, or even people who can program but don't want to write a complicated program, you need a SQL access layer on top of it. So that's really the story of Hive. And Hive, the main use case, I mean, Hive has been in production right now for almost 8 years, I guess. So it's very feature-rich, very mature. It can be used in a lot of different areas, but the main use case is really the online analytics, where Hadoop's strong suit is processing lots of data and doing analysis across the data set, kind of like what some data warehouse tools do. And because it's really been around for so long, Hive has become kind of the de facto standard for SQL on Hadoop, meaning that all SQL engines that are coming out who want to work on Hadoop really look to Hive and try to make sure they support the Hive features. And the popularity is very amazing. Like in Cloudera, about almost 100% of our enterprise customers use Hive. Just again, because of the ease, it allows ordinary people to be able to run these huge MapReduce jobs. So a little diagram of where Hive sits. It's on the top of the stack. So MapReduce is the processing engine backing Hive, and then HDFS, of course, is the storage for the Hadoop file system. So the second part of the story is Spark. So Spark really came as a second wave of big data innovation. The problem with MapReduce, it's very powerful, but it wasn't designed with the general purpose in mind. It was more designed for it was an internal Google project to help them do the search indices. So a lot of projects like Tez, like Flink, like Spark, a lot of these new Buzz projects kind of have a benefit of hindsight to look at MapReduce and be able to do things a lot better than what is being done in MapReduce. So in Cloudera, we have a long time kept our eyes on Spark, and we think it's really the kind of the front runner to be the next MapReduce. And the industry has kind of come to that as well, because if you look at the activity among the Apache projects, Apache Software Foundation has probably hundreds of projects, right, under the umbrella. And by now, Spark is the most active one. And the success of a project in Apache really is the bigness, the largeness of the community. So in that sense, I think Spark really is the front runner. And also around the community, other Apache projects are all moving. A lot of them are moving to Spark. I know a lot of people in this Berlin Buzzwords gave talks about how they're moving their projects over to Spark as well. That are not on this list. So it's very catching a lot of ground very quickly. And the reason Spark is so popular, I think, is just because it was designed with very powerful APIs, very expressive APIs and abstractions, really meant to make it very easy to program a distributed processing pipeline just the way that you want it. So some details of that. So 3 things that I think that Spark can do better than MapReduce and that users of Spark also feel. First is the file, the data format. So in MapReduce, if you remember, everything is HDFS files. It's the HDFS files that are fed into the job and then output of a job. Whereas in Spark, they made a new concept called RDD, which you treat it almost like a file in that you pass it around between jobs. But the point is, RDDs is an abstraction because a lot of times they can be kept into memory. So Spark, being built in around 2009, had the benefit of being around at a time when the systems today have a lot more memory than they did when MapReduce was there. So by having an RDD concept and hiding the fact that you're dealing with a file or in memory, you're really making more benefit of the resources on your cluster. Another advantage of Spark is just the fact that in the programming in Spark, there's a lot of more transformations you can do. So if you ever see a Spark program to do a word count, for example, it's much easier to write than in MapReduce. And also MapReduce has a kind of a design where you have to write a mapper, a reducer, and then the framework executes it in that order, map, shuffle, reduce. Whereas in Spark, you can run things in any order that you want. So you can get a lot more efficient program that way. And we use these 2 quite heavily on Hive on Spark to make Hive run a lot faster. And the last one is something maybe people don't realize is that in MapReduce, every task, so like a map task or a reduce task, are these Java processes. And they all come up when they need to be run, and then they get shut down once the job is over. So if you have 1,000 mappers and 500 reducers, you're spawning and killing 1,500 processes every time. So this is, if you add it up, the JVM overhead can be kind of substantial. For Spark, they again abstracted out so that you have these things called executors, which are long-lived processes, and they can be there and run multiple tasks, so you kind of don't have to pay the cost every time of when you run a Spark job of spawning all these processes and then destroying them. So these 3 things really are just, this is just kind of the tip, but these 3 things we really take advantage of in Hive on Spark to make Hive much more efficient. So it brings us to Hive on Spark, which is the project that we've been working on for probably half a year to a year. And the goal is, well, Hive is a SQL access layer, and as I mentioned, there's probably a lot of people, there's probably thousands of Hive deployments around the world solving real-world problems today. And as an access layer, we want the user to not care underneath Hive what the processing engine is. So by swapping out MapReduce with Spark, we're hoping that they can keep all the functionality that they have today and also take advantage of the new Spark concepts like better in-memory processing, better process latency, and so forth. So the goals, to reiterate, is 1, we want Hive to be able to run seamlessly across execution engines. So the same Hive instance, if you point it to a MapReduce cluster or a Spark cluster or even Tez cluster, should be able to run the same jobs. And secondly, obviously, Hive on Spark, we would need to support the full range of existing Hive features. So that's kind of a background about why we decided to do the project. And the next section is going to be about some technical details about how we achieve Hive on Spark project. So the Hive on Spark, as I mentioned before, the real challenge, it's one thing to kind of build a new system. That's obviously very challenging. But I think for this project, the challenge was to how to port a very mature system that, again, is solving real-life problems today at huge scale onto a new processing engine without any loss of functionality. And there's a lot of functionality built into Hive. If you ever work with a database, you know that the power of the database is how much of the SQL syntax it supports. And SQL syntax, while it's deceptively simple, it can get very complicated very quickly. And also, a lot of times databases, they have things that are not specified in the SQL syntax, things called dialects, SQL dialects. And so people have gotten really used to Hive SQL dialects, for example, because SQL syntax, SQL standard only supports up to some specification. Beyond that, you need your database itself to have this functionality. And other things like data types. So how Hive treats data types when you want to define a int or a string or a char, varchar, binary, things like that. How Hive implicitly casts things from one data type to another. These things people have gotten really used to that we don't want to break when we do Hive on Spark. People might know Hive has a real big library of functions that you can define yourself and then use in your SQL. Like, for example, some mathematical standard deviation function or linear function, something you can define. And Hive has a very big library of those. And also file formats. The fact that Hive has these surdays that you can swap out your favorite file format, like RC file, Parquet file, etc. So all these things, in order to keep the same, what we ended up doing is we try to keep most of the execution code in the Hive operators to be the same across different processing engines. We don't want to rewrite every single operator just for Spark. So the idea is that, in general, we will run the same code that we used to run in MapReduce on the equivalent thing in Spark, which is a Spark transformation. So, for example, in the mapper, if we used to run a filter operator that dealt with a filter function in SQL, now we run the same operator in Spark. Similar in Reducer, we run the same in a Spark transformation. So it's by doing this, we integrate at Spark at a low level and manage to keep all the functionality of Hive. Now, people might be wondering then, like, if we're just running the same code in Spark, where does the benefit come from? And so I'm going to spend the next 5 slides talking about different ways that just by doing this, we can still get a lot of savings in terms of performance for Hive queries written in Spark. And I think this might be also interesting to people who are not Hive users, but just in general want to migrate MapReduce jobs onto Spark, or people who want to write Spark jobs for the first time. This might also give you some insight about how you can optimize things when doing in Spark. So the first improvement is that we can eliminate a lot of redundant phases that we have in MapReduce. As I mentioned before, in MapReduce, if you have a mapper, you have to have a reducer, and in between there's a shuffle phase. So if that doesn't work for your job, and a lot of Hive queries actually go way beyond just one job, you have to have another job. So if you want another shuffle, for example, you have to have another mapper, another shuffle, another reducer. And typical Hive queries that we've seen from customers are probably average 10 MapReduce jobs, and then some really big queries maybe go up to 50 or more MapReduce jobs. So a lot of this is kind of wasted because like between the reducer and mapper, there's really not much there. So if we can, in Spark, because we can run the transformations in any order, we can go ahead and eliminate the redundant phase, and just on the bottom have 3 kind of phases of Spark transformations and run the same code that we used to do in MapReduce. So the rule of thumb is for every stage that you used to have, every job you used to have in MapReduce, we can eliminate 1 phase in the Spark transformation. And so to give kind of maybe an example of this, so one query in Hive that will boil down to more than 1 MapReduce job is if you have, apologize, some of it is cut off, but if you have a join statement, like in the inside I have select key from source 1 join source 2, and then after that I feed that into an order by statement, you're going to get 2 MapReduce jobs, the first one to do the join, the second one to do the order by. But in Spark, we can just do it in 1 big Spark job, and also combine the first reducer and second mapper into the same transformation there to get. So we actually run the same operators that we used to run, but now we eliminate a whole stage in the data pipeline. using just by using Spark. So that's some savings, pretty significant savings, and it actually gets better than that because, as I mentioned before, in MapReduce, there's this concept of files, and every MapReduce job will write out this huge file, and then the next MapReduce job has to read back in this huge file, just because that's the only way for the two jobs to communicate with each other. And in fact, in Hive, if you ever used Hive, you have to define a temporary directory where what it really is like the partial results from one MapReduce job are kept there, and then they're read back in when the next MapReduce job runs. So in Spark, again, this problem doesn't exist anymore. One, because we've combined the reducer and mapper, so really there's no need to kind of channel data from one job to another. But even when we do, like for example, from transform to the shuffle to the transform, where we do need to pass data along, we use the Spark RDD concept. So Spark already anyway keeps that into the memory. So the way RDD works is unless you explicitly ask to spill to disk, or if you run out of memory across all your processes, only then does it spill to disk. So if you configure enough memory for your cluster, a lot of this stuff can be kept in the memory and at very low latency when you move from one transformation to another. So that's another improvement that we can achieve by doing the Hive on Spark. Running the same operators, but at a more efficient transformations. And kind of the next one is the shuffle phase. So this is the last thing I'm going to talk about for the execution part of the Hive code. So inside, so that was talking about if you have more than one MapReduce job. Even if you have one MapReduce job, there's a shuffle phase that we can improve on. And if you know a little bit about MapReduce, you know that shuffle is really, after the mapper is done, the output is kind of shuffled to different nodes and then sent to the reducers. So a lot of MapReduce jobs, this is one of the more expensive parts because shuffling, I mean, it's not file I/O, but it's still a lot of network I/O. You're still moving around potentially gigabytes or terabytes of data across the network. So in Spark, you can't get around shuffling, but you can do, sometimes you can get more efficient shuffling because MapReduce, in my next slide, so MapReduce has only one thing called a shuffle sort. So when the shuffle phase happens, what it means is that it does a hash partitioning of all the data, and then it sorts each of the partitions. So this works for all the problems, but then it's sometimes, in fact, a lot of times it's overkill for what you want to do. So to give some examples to help illustrate that point, so for a query like select, so it's an aggregation query, if you know SQL, so the point is you group by a key and then you select average from each key group. So basically in this example, we don't really need to sort each key group. After you have all the rows of the same key in one group, all you need to do is take the average of them. But in MapReduce, it will do secondary sorting anyway, which is a little unnecessary and not able to turn off. So in Spark, you can call, just by calling a different transformation, shuffle transformation, like group by, you can get the exact behavior you want, which is just to hash partition by key. Just make sure the data rows with the same key go to the same partition, and stop at that. So we get some freedom that way. Another one is the order by. So another example is select key from table order by key. So this query means you just have, you have this huge table and you just want to get a total order sorting of it. In Spark, you can call an order by transformation that does that in parallel. So Spark has already, just by calling this API, has a lot of logic already to do. So what it does is it takes samplings of all your data, makes appropriate range partitions, for example, 1 to 10, 11 to 20, and then have the data partition in each range and then parallel sort those to get a total sorted result. In MapReduce, the traditional way, if you wanted to write a sort in MapReduce, is you just it's kind of a stupid way. Is like you actually just partition everything to one partition, and then the MapReduce anyway sorts all the partitions, so you get it sorted by default. But it's in serial instead of parallel. So again, by running this transformation in Spark, you achieve more savings for the shuffle phase. So that was that was all I had about the execution part, just the fact that between MapReduce jobs and inside MapReduce jobs, just by using Spark, we're able to achieve a lot of savings that way. As I mentioned before, the second part is this process lifecycle. So if you remember in MapReduce, all the mappers and all the reducers are actually one process, and then when they're done, they just shut down. So a lot of the MapReduce job is just spawning and killing processes. So in Spark, again, the executors are what they call processes, and they're quite long-lived, and they can run one or more tasks. And another terminology in Spark is called an application. So a set of executors for a given user is called a Spark application. And a user can choose, how many executors he wants, tune it so that he can increase or decrease it. And so what we do in Hive on Spark is that for every Hive user session, so every time you log into Hive and you run a Spark query, we're going to start a Spark application for that user. And based on what you configure, we're going to pre-start that many executors for you, so that only the first query will incur the cost of starting all these processes. Subsequent queries will just reuse the processes and not pay the cost of spawning all these processes. So just to give kind of a graphical thing about what I talked about, in MapReduce, every stage will have a lot of process kind of life going up and down. But in Spark, what you do is you define for a given application like initial number of executors, the minimum and the maximum, and then, or you can even give us just everything is the same number, and then the number of processes stays more constant throughout the whole Spark jobs. In fact, across the whole session, in multiple Spark jobs, processes don't need to be spawned anymore. So that's kind of for the technical part. So for the user part, so I'm just going to spend a little time talking about, after that, what kind of results we got and how users might be able to leverage Hive on Spark if you are a Hive user. So to leverage this thing, again, we try to make the installation not as more complicated than it is today. So anyway, when you install Hive today, you have to install first Hadoop, which is the file system. Another thing is Spark can actually run on different resource managers. So there's Yarn, there's Mesos. And these things, what they do is they make sure that users of Spark, different users of Spark, don't collide with each other, and that their jobs are scheduled properly. So we recommend in Cloudera to use the Yarn mode, and in fact we ship with the Yarn mode as default. So the reason is it gives you a little more control over the number of processes that an application can have. So all this stuff of dynamically increasing or decreasing the number of processes is only in Spark on Yarn mode. And so the only extra step here is you have to install Spark, and then after that you install Hive, which is, so if you've ever installed Hive before, you know that if you install Hive on a MapReduce node, and that Hadoop node has configurations, it will just pick up those to find out where the MapReduce master is. So similarly, when you install Hive on a Spark node, it will just pick up from the Spark configurations where the Spark master is, what the Spark serializer is, so forth. So you really don't need to configure anything. The versions you have to run with, these are the ones that the latest ones that we ship with is these versions here, Hive 1.1, Spark 1.3, Hadoop 2.6. If you download the latest Cloudera 5.4, in fact, we actually ship with all these versions, so you don't have to worry about compatibility issue. And then the Hive client, all you have to do is set the execution engine to Spark. As I mentioned before, one of our goals is to have the same Hive be able to run jobs in MapReduce and Spark. So you can switch, in fact, dynamically what cluster you want to run your job with. Then you just run the query. And keep in mind, the first query may take a little more time to execute because we're pre-warming the cluster and starting up these executors. But subsequent jobs will be able to reuse the executors and get a lot of performance benefit. So when you run the job, if you ever run a Hive job, you run the job and then a lot of logs come. And basically, they used to show the MapReduce job status, like how many mappers are running, how many reducers are running. It looks a little different in Spark, but the idea is the same, just how many Spark tasks are running at any time. So not too much different there. Then in the Spark UI, the Yarn UI, you can actually find the Spark application that you started. Click on that, and then you're able to drill down into the Spark UI, which is, again, it's a little cut off, but the Spark UI will show, it kind of shows the same as what the console prints out in terms of job progress, but you can click to see more details about what tasks are running, how many are there, and also like environment variables, executors, what everyone's doing, and so forth. So pretty easy to monitor your job also on Spark. And things you might want to tune. So again, I talked about a Spark application, how it pre-starts a number of executors for you. And the idea is you can set like a constant number, which is static allocation, or on Yarn mode, you can set a dynamic number. So the two differences is if you set a static number, obviously everyone gets 10 executors. Okay, well then the performance is going to be more stable because you're always going to run on those nodes. But then you might end up with some users not being able to get in because if 10 people already allocated 100 executors and you only have 100, then the next guy will have to, he will not be able to get any resource. So dynamic allocation is a better way. There's slightly more unpredictability for performance, but then what you can do is you can specify a range. Like I start at 1, but I can go up to 10, and if no jobs are running, it will go back down to the minimum number. So these are two options you can use in Hive to tune Spark. In fact, even if you don't use Hive, you're just running Spark jobs, you can use these two options to tune how many executors a given application has. And then again, Spark executors, another thing to tune is like the memory. So the memory will affect obviously how much can cache into memory, how much of the data of the RDD can be kept into memory. So this affects the performance. So Spark has kind of a lot of settings for memory. One is the cores, but also has memory settings, and then another one is the driver, which is the Spark, like the master executor, I guess. And you can tune that one. Maybe it has a little more. So you can tune those. So that's kind of it for the user view. If you want to play around with Hive on Spark. Now, I'd like to share some performance benchmarks that we made. So we have people working from Intel China, and they helped us do these benchmarks, so I'm just taking their numbers. So they played around with a cluster of 8 nodes, where every node has 32 cores, 64 gigs of RAM, 10,000 megabytes per second for network. So kind of a little large, but typical like a data center configuration, and these are the versions that we use for the different components. And we played around with the TBC DS data sets with 2 data sizes, 320 gigs, which is kind of an average data size, and 4 terabytes, which is a little on the larger side. And TBC DS is, if you don't know, is the standard kind of benchmarking for all the SQL like databases use it quite heavily, and now some of the big data on SQL solutions are also using it. So, and we also have some of these configurations that we enable to make sure all the processing engines get equal kind of play. In fact, maybe as an interesting side, like all these optimizations that are in Hive code is able to be run across different processing engines without any loss of functionality. Memory vectorization, for example, is just to make sure the Hive operators, when they do loops, that there's in such a way that they can benefit from the multi-instruction of a CPU. CBO is the fact that you're, so in all the execution engines, we're running the operators in the same order, but CBO makes sure that the operators are run in optimal order. So it does things like maybe reorder some join or push down some predicate to the front. And then finally, the last one is kind of a strangely named flag, but what it is make sure some joins get turned into map joins if there's enough memory. It's a different join implementation that's a lot faster, but you have to have enough memory to do it. And so not going to spend too much time, but these are the kind of the Intel guys set to make sure that both these Tez and Spark are tuned very properly. And again, because the first query is the one that kind of pre-allocates a lot of these executors, what we do is run each query twice. So the first is to warm up the cluster, and then the second is the one that we actually measure the results. And so not only Spark has this issue, but even Tez. Tez has something called pre-warm containers, which is basically the first query will spawn a lot of containers up, and then the second one will be able to use those. So for 320 gigabytes, we have some nice results. I mean, we don't beat, so we beat Spark. Hive on Spark is faster than Hive on MapReduce for all the queries. But I mean, and then we're faster than Hive on Tez on a lot of queries, but there are some queries that we're still working on to catch up to Tez. And if you look at 4 terabytes, the results is more pronounced. So I mean, the ratios is mostly the same, but then the gains is more pronounced. And that's just because, again, I mentioned a lot of the savings we have in Hive on Spark is, not flushing everything to disk or not shuffling everything in a kind of a inefficient way. So if the data is more, you actually get more savings from some of this stuff. So and Tez, so I think what they did is some of the range is a little small. So they blew it up and then just have another comparison for Spark versus Tez. So so for most of the queries, we're faster than the Tez, but some of them were slower than Tez. And I'll talk about that in the next slide, which is, so Spark is faster on most queries. We're working on some optimizations to make Spark faster for some queries that are slower than Tez. Some things like dynamic partition pruning, which is kind of a Hive concept. It means when you join 2 tables, you can prune away some partitions of another table based on the fact that the first table, only has these join keys. So you don't actually need to read these partitions of the second table to join. It's kind of a more advanced optimization that we're working on for Hive on Spark. In fact, one of my colleagues is already working on this and has a patch ready. And Spark is also kind of a newer project. So some of the shuffle sort that they do is not as fast as it could be. So, but the real benefit of Spark is not like that Spark is fast today, but also the promise that Spark can be faster in the future, just because it's such a healthy and a vibrant community. And they already have a lot of things in the works, like shuffle sort improvements already in the works. And then they have things like Project Tungsten that can promise to do a lot of more improvements for Spark. So we're very confident that just by doing this project in the future, we're going to get even more benefits for Hive users on top of Spark. So, okay. So actually, I'll leave some time for questions. So actually, it's perfect because the last slide is just to say that Hive on Spark is available in these versions, Hive 1.1 and CDH 5.4. And if you want to look at the code or any of the work we did, Hive uses the Jira system. So Hive 7292 is the Jira, umbrella Jira for all the Hive on Spark work. And then it's not just a one company effort. In fact, we had many companies like Intel people from China, IBM, MapR, some help from Databricks, and from our company too. So it's kind of a joint effort. And yeah, so I think that's pretty much all I had. So I'll leave time for some questions.